Okay, we're going to do section 5.3, which is the definite integral. Okay, so we're going to start off with notation here. Okay, so this is our integral symbol. Okay, it's kind of a long stylized S. Okay, and it does mean sum. The idea here is that we're adding up all those little bitty tiny pieces. We are going to go from A to B. A does need to be lower than B. This is our function, and then this is the variable that we're taking the integration with respect to. Okay, so now if we are looking at kind of a stylized, since I told you it was a sum, okay, this is the summation from n, as n approaches, or sorry, okay, let me clean that up a little bit, put it back. Okay, so here is the idea. We're going to let n go to infinity. That means the number of rectangles. Okay, so we're going to the number of rectangles to go higher and higher and higher. Okay, and so we're going to start at the first rectangle and go to infinitely many of these rectangles. And it's going to be f of a. So basically what we're starting with here is on a function. Here's a. So we're going to start here, and then it is the k up here tells us which rectangle we're on. Are we on the first rectangle, the second rectangle, the third rectangle, so on and so forth. The interval over n, okay, so that tells us how wide to go. That f of that is going to give us the height of our rectangle, okay, and the b minus a over n gives us our width, okay, so that would be like our first rectangle, and then we go up to the second rectangle. Again, the idea here is that when these rectangles get really, really, really tiny, I no longer have that over guess or under guess stuff that we had before, okay. So now then, now one of the things that we have is if f is our function, bring this over into play here. F is a function, okay, and it is continuous on A to B, okay, so it's closed interval A to B, or it has finite jumps, discontinuities, okay, then we can do the definite integral from A to B exists, and then we say f is integrable over A to B. Okay, now I'm going to come back to this jump, this finite jump discontinuities, as we process a little bit forward over the next little bits, okay, and it'll make a little bit more sense when we pull that in with one of the rules here that we have, okay. So now what we're not going to use is f and g are integrable on A to B, okay. Then we have the next several things hold up is true, okay. So one of them is if they switch the order, okay, if they switch the order, so it should be A on the bottom and B on the top, so low to high, then you can switch it to low to high, but you have to pick up a negative out in the front end. Okay, now if you integrate from a value to the same value, this is 0. Okay, the idea here is if you integrate from a value to a value, you have integrated a line. Okay, there is no area to a vertical line segment. Okay, so there is no area to that. Now, we saw, and some of these rules we saw in differentiation. Okay, so if you've got a multiplier on the inside, you can bring that out to the outside. Okay, so you're allowed to do that. You can also do, and they combine these. Okay, so if you have like a function plus function, think polynomial, we're not actually going to break it and show it in separate parts, but you do each part independently as you want to. Now, this next one, okay, no, sorry, a to b of f of x dx plus the integral from b to c of f of x dx is going to roll from a to c of f of x dx. And I'm going to move up so you can see that. Okay, so here is the one about when you handle that finite number of jump discontinuities. If I'm going from A to B, and then I go from B to C, and again, assuming here that we're integral on B to C, then that's also from A to C. Now, the way this works is if on the integral from A to C, I have a jump discontinuity, then I'm going to break it into the two parts. Okay, I'm going to go from the beginning to the jump, and then I'll pick up from the jump to the end, and that'll give me the whole thing overall. Okay, now another couple of things that go with this. Okay, if there's a minimum value on F and a max value on F, okay, so we have a high and a low on F, okay, if I take the minimum value of F and I multiply it with the length of the interval, okay, that is going to be less than or equal to the integral from A to B of f of x dx, and that is going to be less than, then the max value of f times the interval from A to B. Okay, and I'm going to show a picture of this one here in just a second. Okay, now the other thing is if f of x is always greater than or equal to g of x, okay, so it's always higher, then the integral from A to B of f of x will always be greater than or equal to the integral from A to B. Okay, now if f of x is always greater than 0, meaning the function is always above the x-axis, okay, then the integral will also be greater than 0. Okay, so we're going to look at a couple of pictures, okay, of just a few of these. Okay, I'm not necessarily going to do all of them, okay, but I am going to do a couple of them. Okay, so the idea here is, I'm going to talk about that one. If this is A and B, and then this is C, okay, the integral from A to B of f of x dx is this area. Okay, the integral from B to C of f of x dx is all of this. Okay, so if we think about the sum, okay, how to find stuff, if I want to do the integral from A to C, then I can do the integral from A to B plus the integral from b to c. Okay, so you're allowed to do this kind of addition of parts. Okay, now normally we see this, they want us to go from a to c, and we wind up cutting back some stuff. Okay, now the idea for that max min one. Okay, let's say this is our function. Okay, and we're wanting to go from here to here. Now this is our min. Okay, so if I take that height, and then this is a to b, okay, min of f times the interval, oops, sorry, is going to be that green part down there. Now, this is our max up here. And so if I make a rectangle box, okay, so max of f times b minus a is the stuff in red. Then the actual function area, or area under the curve, which is kind of all that purpley color that I squiggled in there, is going to be someplace in between those two. Okay, the green's too small, the red is too much, the purple is the exact answer. So it's going to be between those two values. Okay, now we're going to take a look at a couple of these rules in setup, okay, and see how they work. So we've got, these are just some things that they're telling us. -1 to 1 f of x dx is 5. The integral from 1 to 4 of f of x dx is -2. And the integral from -1 to 1 of h of x dx is 7. So the first thing that they ask us to do is the integral from 4 to 1 of f of x dx. Okay, so we notice that our interval bounds are out of order. That means that is the negative when I switch them, which means that is negative, and then looking from 1 to 4, that was -2. So that's going to be 2. Okay. Looking at another one, -1 to 1 of 2f of x plus 3h of x dx. Okay, now they've got a couple of things going on here. One, they're adding functions. Two, they've got multipliers. So I'm going to bring this all kind of, so we're going to do the integral from -1 to 1 of f of x dx. And you do need to make sure that you've got dx on every integral that you're doing, plus 3 times the integral from -1 to 1 of h of x dx. So now running this, the integral from -1 to 1 of f of x was 5, plus 3 times the h of x1, which was 7. So we've got 10 plus 21, which is 31. So there's our answer for that one. Okay. And the last one for this set is they want us to go from -1 to 4 of f of x dx. And this is where you're going to see that we're going to split this. So this is going to be the integral from -1 to 1 plus the integral from 1 to 4. Okay, so this is 5 plus -2, which is going to be 3. Okay, now, I've already hinted at this next definition, okay, but the area under the curve y equals f of x from a to b, or over a to b, sometimes I use, is the integral from a to b of f of x dx. So if they ask you to find the area under the curve, all that means is find the integration. Okay, now I am fixing to kind of jump and kind of give some clue out, well, we'll start with the ones that they tell us, okay? So some just rules that they let us know. Okay, now, I am going to go ahead and jump, okay? Guys, the idea here is we're doing that because we've already done this, okay? So we think about where this is headed up. Where does x have to integrate back up to? X has to go back up to an x squared, okay? And then I need a 1/2 out in the front of here, okay? Now what happens with this is you're going to plug in the upper bound and the lower bound. Now, yes, there's a plus c. So now let's talk about what happens. When we do the definite integral, we're plugging in the b and we're plugging in the a, and we do upper minus lower. So this is going to be 1/2 b squared plus c minus, and I'm going to do a big set of parentheses here, 1/2 a squared plus c. So it's going to be 1/2 b squared plus c minus 1/2 a squared minus c. And y'all, that's the same c. So those are going to go away. So now I have 1/2 b squared minus 1/2 a squared, which is b squared over 2 minus a squared over 2. Okay. Now then, another one that they're going to do, and we're going to expand on a lot of these as we progress forward through our integration, is if we do a constant function. So if this was a 3, okay, guys, think about this. That's going to go back up to c times x, again, plus a big constant. So that is going to be, and again, we plug in upper minus lower, so that's going to be cb plus the big constant minus ca plus the big constant. So this is cb plus c minus ca minus c. Again, the c's are going to cancel off. So I have cb minus ca. They indicate that this is c times b minus a. Okay. So another one. And they send this as b cubed over 3 minus a cubed over 3. Okay, so again, think about where this integrates back up to. Again, we're doing the opposite here. X squared has to go back up to x cubed, but I need a 1/3 out in front, so when that 3 multiplies down, I don't have anything left. We talked about we plug in upper minus lower. Okay, and again, we would have talked about that this was plus a c. I'm going to get into this here in just a second. So now, if I plug stuff in, that's 1/3 b cubed plus a constant minus 1/3 a cubed plus a constant. Now, what you may have noticed is on every single one of these that I've done, that big plus a c has wound up getting subtracted. What we're going to see is when they formalize the definition, they're not going to have the c's there, okay? Because they always happen to cancel off on both of them, okay? Now then, one other thing that comes out of this section, okay, is the average value on A to B, okay? Sometimes this is also called the mean, okay? Keep in mind, average and mean have often been used coincidentally. Now, notationally, they call this AV of F, so it's the average value of F, and what this is equal to is 1 over B minus A times the integral from A to B of F of X dx. Okay, so the concept here is if I have a shape, okay, and I figure out the area under here, whatever this is, okay, and then 1 over B minus A. Basically what we're doing is we're turning this into a rectangle, okay? The idea here is like we take like some of this, we chop some of this off, and then we use it to fill in over here, okay? So we take like this up here and we fill it in over there, and we have a rectangle. So if this represents this area and I divide it by the length, then this becomes the average value, okay, going up, okay? It kind of hits, we hit the high values, we counteract with the low values, and overall it gives me that, okay? So that is the end of this section.